Welcome to the Human Factors and Ergonomics Hub, a series of educational podcasts that showcase the connection between human capabilities and good work design, brought to you by the Human Factors and Ergonomics Society of Australia. It's so great to be back with you on the HFE Hub. I'm Sharon Todd, and we've just had a short break, but today I'm back talking to Paul Lambertson about human systems integration on flight deck design. Now, the views expressed in this podcast are Paul's views. They are not the views of Boeing, any other employer or person with whom he has worked. Thank you so much for joining us today on the HFE Hub. I'm really excited to be chatting with you because you've got a really interesting career, which we'd love to hear about. So maybe you could just tell us a little bit about yourself, where you're working and what you're doing.
Sure. I'm currently working at the Boeing company. I've been there for 20 plus years, and most of the time I've been there, I've been working in the flight deck area and with a focus on flight crew operations. And during that time, I've been able to lead several teams, which I'm actually really grateful to be able to led. And among those teams, I've led the optics and lighting team, the test and integration team, human factors, ergonomics, and human systems integration strategy. Currently, I'm a lead engineer for product development in the area of simulation and technical analysis for the flight deck. And at the moment, just recently, I've been placed as one of the chairs of the INCOSE Human Systems Working Group. So that's kind of the brief where I'm at today. I did start in the automotive industry, and one of the reasons I'm now in aerospace is I can thank or blame my grandfather, because he's a World War II veteran that was involved in the Air Force, and then he went and started building planes and made me interested in it. So it kind of got me all interested in aerospace.
So how did you get into aerospace, really, or Boeing? How did that opportunity arise?
Well, that actually arose from actually a friend. I was always kind of interested in Boeing, but I was actually started off working in Detroit on the automotive industry, and a friend said, "Hey, Boeing is hiring, and they're hiring in areas that you'd probably like," which he kind of mentioned both flight controls and flight deck, because they're both areas where you can have a lot of human integration and human systems work with. And I went over and talked with them and ended up, after several conversations, ended up working for them. And since then, it's been a very interesting and sometimes very fun job, because I've been lucky enough to work on pretty much every Boeing commercial model that is out, and some of the military models. So it's really been interesting and enjoyable to work on all the different Boeing products.
You've mentioned simulation and technical analysis is an area where you're working at the moment. Could you tell us really what that's about?
Well, that is about a lot of different things. It's everything from the possibility of virtual reality to new tools such as the STPA, which is a systems theoretical process analysis, and working requirements into the system. And it's from my standpoint, it's really focused on the tools and simulation that input between the human and the machine. And that's the focus, and that's really the focus of what the crew operations team does that I work in, is the man-to-machine interface. And so all the simulation activities we work on, which involves everything from, say, a computer code on the desktop to a flight simulator to even potentially testing on an aircraft, and everything kind of in between. So it's very large on that. And then also part of the function that I'm in is the tool. So that would be things like the model-based systems engineering tools, the STPA I talked about, and those types of analysis tools where we can analyze information before we have a design or before we have a full set of requirements and that type of thing to get information on that design or those requirements.
So before we chat about that, just a quick question is, what part does human factors and ergonomics play in the work that you do or in flight deck design? These are for people that may not work in this space.
Yeah, well, in the flight deck design, the crew operations I'm responsible for it's really the interface between the pilot and the flight crew. So those would be things like the displays, the seats, the various fixtures in the flight deck, the controls, everything like that. And some examples of the things that we work with would be like components for ergonomic analysis. Say from the seat, you have to be able to reach all the controls. So simple, well, it's not always that simple, but on paper it looks simple, is the ability for a person to reach all the switches and components while they're seated. So that would be one of the types of things that would be looked at. And another thing that's actually can get really complex is if someone can imagine when they're in a flight deck and it's bright and sunny and they're trying to look at the flight deck displays, which are basically kind of like TV displays. So if they get hit by a lot of light, they can get washed out and hard to read. And we have to manage those designs so that they're still readable in bright type sunlight. And that's actually quite a bit trickier than some people might actually think, because of how the sun can come in if you're in an aircraft from various different angles, and making the flight deck displays able to be in essence shaded from that sun can be quite a challenge.
I mean, you can't exactly pull the blind down, can you? So what are some of the things you have had to come up with to solve those problems in glare, particularly?
Yeah, one thing that helps, but it's not perfect, is coatings. Another thing people can do is in essence find ways to shade the displays from the sun. So like putting bezels or something in places that block the sun from directly hitting the displays, or designing in the displays in a flight deck so that they won't hit as much, be hit by light as much as if they were just straight out there. And so it actually takes quite a bit of analysis, and there's even the software out there that we can use for shadowing and effects of lighting that have helped us in our initial concepts for.
So let's go back to the design, and you indicated that there's a certain amount of analysis that's required before you come up with a design. So let's talk about how you do that and what you do.
Okay, well, it pretty much, when it comes to the design, really starts with finding the requirements and getting those together from a sense of what is it we want to do. So I follow the principles of human systems integration, and that really means the design is integrated with the people, the technologies, and the organization. And so when you do it that way, there's things which are really difficult, and they're really very much human in the human factors environment that we can start to work with. And one example is every airline customer company has their own version of a electronic personal electronic device that in aero speak, which we love our acronyms, we would call a PED, a personal electronic device. And this could be something like an iPad or a Surface or even something different. And so the airlines can use that data to perform all their flight planning or simply do stuff to integrate their performance data. We in the crew ops would have to get that type of thing, taking software that we haven't designed or may not even know completely how it works, and be able to let that integrate into a flight deck. And so those are the kind of challenges and the design concepts we have to deal with. So it really involves sometimes everything from doing anything from surveys or interviews to understanding the basics of the technology that's going to be used, and then and then understanding even a little bit into how that organization wants to use it. What do they want to get out of it so that we can bring it in for their use. And then it even expands further because it means it's not just one airline. And since there's differences between every airline, it's trying to understand the whole picture of how everyone wants to integrate it. And that is the really, I'll call it the difficult point of how we have to go, because when you do that, you have to start to make trades between the different environments and how things work. Because of the wide variety, you can only accommodate so much. So you can't always get 100% of what everybody wants. So you have to figure out what the best is from the human standpoint, and that's part of the tricky part of how we work through our designs.
Yeah, because obviously compromising, could be dangerous. So you want to make sure that it's the right thing. So that leads nicely into the reason why you use simulation. So talk to us about how you use simulation to help you with the designs, particularly where you're trying to look at software and integration.
Well, simulation, some of the first really nice things we can do is, if say the example I was talking about with the PEDs or the personal electronic devices, we could do integration work on, say, a desktop computer and start out looking at the requirements we've developed from, I'll call it the customers, the users, and the regulators, because they're all, that's one thing that a lot of industries don't have quite as much of, but we have to take all those regulations into account with when we design something too. And so we're really able to push the simulation through a desktop and then work through it. Part of it is working through rapid iterations, which we can do in several areas. And then as we go to, I'll call it a higher fidelity simulation, like say a flight simulator or something more towards that, it starts to be a little harder to iterate. But the nice thing with that is we can fine tune things to a large extent, and then kind of really get more into our verification testing as we get to the higher fidelity facilities. So that kind of helps us where in the lower fidelity, we can still get together with the users and develop items and work through what I'll call rapid iterations, and then go to the higher fidelities where potentially we have real hardware in the loop. And so we have, say, actual avionics software with the personal, the PED device together, and those would function just like they would, say, in an aircraft. And potentially we would even take some of it to an aircraft at some point. But ideally, most of this and our studies would get completed before then, and it would all turn into validation. Did we actually get it right using all the information and assumptions that we worked on beforehand?
So you've talked about software that obviously may change from aircraft to aircraft. Are you designing that software or modifying that software, or is it more likely that you're given software and then you're trying to make it work?
Well, and the answer is that could depend. If it's one of these PED devices, we may have to say a specific airline has something they use. We may have to see if we can get that to work properly, or in some cases, particularly if we're at the start of something, we could have programmers working with us in a true human system integration activity where they're actually writing code and updating it as we're finding updates to the requirements and going through the iterations. And so there's really a wide variety of what can happen in the aerospace industry, and probably I would say in a lot of industries, because it's somewhat similar in the automotive industry too. And with that variety, you have to really, it changes how much you can actually impact. And it comes down almost always to trade studies, because you want the software from a human engineering standpoint to kind of work well, fly just right. And it does turn down sometimes because of limitations on you have to use a customer software and other things. You can't always get everything you'd want. So you want to make it as safe and usable as possible. And there's always that kind of trade in automotive, aerospace, and pretty much every industry. And that's what we have to work that balance.
And I imagine, given that there's been plenty of airlines before aircraft, before the aircraft that you may be designing, that there's a lot of feedback that's being included in the analysis process.
Yeah, we're actually in many ways, I think any industry that's kind of established already has the ability to hear the good and the bad from their customer base. And so that's something that I think is critical for really any industry, is to understand as much as you can your customer and what their needs are, and how you can, from the human to machine interface, make that happen efficiently, effectively, and how they would, and in a way that kind of makes it pleasant for them so that they can do things very efficiently and feel productive.
So you've indicated that you're using systems theoretical process analysis. Let's chat about what you're doing with that and how you found that working for you.
Yeah, and this is actually something really interesting. And what I probably would like to do to give people an idea is tell a couple stories about it. Originally, STPA, people may or may not know, it started from MIT, and they developed a theory and based it out. But to give you an idea on what it helps find is kind of like, imagine yourself taking a high performance jet fighter across the ocean, and I would say you're fortunate enough to engage in a simulated dogfight with some of the other people taking that across the ocean. And when you do that you arm a missile, and you intentionally arm a blank missile, but your aircraft does have real and blank missiles armed on it. And then you lock and fire what you believe is a blank, but because the airplane has automated systems that use the best firing solution possible, it finds out that one of your other missiles is the best solution and fires that missile at, in essence, one of your friends. That can be quite horrible, and something similar that happened in real life. And the catch to that is that worked exactly as the aircraft was designed. The human did exactly what they were told and trained to do. And the system overall, the human, the aircraft worked exactly like it was supposed to work. And yet an unintended effect happened. And those type of what I'll call integration issues between, particularly with my job, the human and machine, are things that can be found with the STPA. And that type of thing to me is very dramatic and real. If we can find those type of problems even before we have a design, that's huge. So I'll give maybe one other example to allow people to maybe sink it in. In the Pacific Northwest, where I'm from, we have a lot of ferries and actually a fair amount of tourists. And during that, a regular tourist would come in, say, rent a car from the airport and decide that they want to go to one of the beautiful islands in the Pacific Northwest or a peninsula or someplace. And so they get on it. They'd park the car on the ferry, and the ferries are large enough here that they have sometimes 2 or 3 decks. And so most people, particularly if you're a tourist, you get off, you enjoy the view of the ocean and the mountains and all the wonders. And then you come back to your car and it doesn't start. And what happened here, and this is something that actually happened here in the area, is the rental car agencies were getting some car thefts. So they decided to put in a design where their car, if it starts to move and the engines are off and there's no power, it'll, in essence, a security feature will kick in and lock it out so you can't start the car. And they didn't put into account what their users were going to do with that car. And a ferry, what does it do? You park your car, you move across the water, and so it exactly hits these results. And that actually ended up jamming up the ferry system in the Puget Sound area for several days. And that is really directly related to a user experience, or you can put it also as a concept of operations, how that would be operated, which is another way that STPA can also pick up those type of problems. So those 2 things and examples really, from my view, emphasize how the human in the loop can be used to find issues. And that is one of the things STPA, compared to a lot of more traditional analysis, says you can actually put the human as part of the system. And that's not the normal way that is analyzed and or worked. Most systems use the human as an actor. So that really shows the power that can be found, because those are 2, what I would say, traditional analysis won't find those kind of problems. Like, you won't find that type of issue doing an FMEA. You really won't find that type of issue doing an FHA and various other things, other analyses that can be performed. And so that's one of the things that really highlighted STPA for me.
For those that haven't used STPA, can you explain how it works or what the essential elements of that analysis process?
And so STPA is based on control loop theory, and as that, it's based on control. So it's based on, I'll call it in essence, an action and a reaction. And so what a person first does, and we'll keep it, since we're not showing pictures and stuff, very simple, is you scope the project. So it's kind of like, what are you going to analyze? In this case, we'll do something simple like a pilot and their ability to pitch an airplane up and down. So if they're going to do that, the pilot is the control. So the pilot controls the process, and the pitch up and down is done in essence from a stick or wheel and column. And then that information is fed back from the controller via, in the case of most modern airplanes, some type of display, or you could even say out the windows, where in essence, trees get bigger or smaller depending on if you're going up or down. And then and that would be a really simple control structure. And in that, you define what your losses would be and your hazards. So you define like and these are things you don't want to happen. Like if you went pitched up or down too much, you could end up losing an aircraft by either hitting the ground, or if you pitched up too high, you could stall and then lose control and end up hitting the ground again. So those would be the things you'd want to prevent. So that would be kind of the losses. You don't want to, in essence, in this example, want to lose the aircraft. And then once that's defined and we've got a simple control structure, and I should note these control structures are all kind of an abstraction. So you want to go to the level of abstraction that you've scoped your project to. And we're keeping this example super simple. So it's the pilot pitching up or pitching down on the controls, and then the feedback from the controls telling the pilot how they've pitched up or down. And then from that, you identify what is called undesirable control actions. And so things like providing a pitch up command would be unsafe if the aircraft is unable to maintain that speed and could result in a stall. So, i.e., the pilot pulls up on the wheel column or stick and so hard that the airplane doesn't have enough speed to maintain lift, which would, in essence, or could bring the airplane to the ground. And so then that would be an undesirable control action. And then you'd identify how could that be caused. And in this simple example, you could cause that control action by just the pilot being unaware, meaning they weren't trained on what the maximum speed and pitch angle are of the airplane, and that could cause a stall. So somewhere in the system, there is a fault that causes the airplane to stall by pitching up from and then bringing the airplane down. And that could be several things. It could be the indications aren't provided to the pilot in a timely manner. I mean, it wouldn't be very useful if, say, the pilot's pitching up, but 20 seconds after you pitch up, or even longer, the controls finally say, "Oh, by the way, you've pitched up 20 degrees when you're only supposed to pitch up 15 degrees." And so using that type of analysis, it helps, in this case, the simple example, it helps us understand what could go wrong, and then we can write requirements on what can go wrong. So then in the simple example, we'd be able to use the data from the unidentified control scenarios and the undesirable control actions to create requirements. And they would be, which I love, they'd be human factors type requirements, things like the pilot shall have an awareness of the pitch of the airplane. I mean, that would be a kind of example of what types of requirements can come out of that. And these would be human to system or even system to human type requirements, which in almost every industry that I can find, those type of requirements where you involve what's delivered to the human or what the human's delivering are kind of rare. And so this tool really helps bring that factor of what the human should be doing, what the human should be provided with, and how the human should be able to see their environment to ultimately enhance safety. That really is huge. And in fact, I think it's because it's one of the things that's been so interesting about it, STPA From my perspective, is recently the FAA, which is the Federal Aviation Administration, and EASA, which is the European version, ICAO, and NASA, and one of the South American regulators all actually agreed that STPA does several things that the current tools don't do. And while this is specific to the aerospace industry, it really can help reflect for everybody in any industry that when you get these many regulators and industry leaders like NASA to kind of agree on something, it is worth anytime I see something like this, it's worth a second look, because they rarely fully agree on anything 100%, it seems. And so that kind of pops out to me when those type of things happen. And that's really helped, from my standpoint, get momentum going in my area to look at this, because some of the things they've said, like STP addresses important gaps that exist in the standard approaches for safety that's used today. And when we see like the simple examples I did, you can, and the talk about not having human system requirements in general. I mean, when you look at, I don't know, most papers I've read on requirements and stuff rarely try even attempt to do a human to system requirement, and when they do, they don't normally take into account the things that could go wrong. It's more, I'll call it, from a user experience standpoint, which is actually very awesome, but it's a start. And so that really drove STPA home for me. So I'm hoping people listening to this will take a little stronger look at it also.
Yeah, I can imagine that the crew would also be pretty excited about this type of analysis, because I imagine that it's looking at some of the mental models and decision making that they would employ to make decisions about whether they're going to go higher in the aircraft or lower in the aircraft. What is some of the feedback that you've had using this tool?
Yeah, and actually one of the neat things using this tool, you can actually have the users, meaning like in my case, the pilots or the design engineers of the specific areas, directly involved. And the feedback has been pretty incredible. There's been a lot of feedback on wow, we've found things that we've sometimes talked about, but we've never put them in requirement words. And then it's like, wow, that's an incredible requirement. And the feedback has just been outstanding from everybody who's looked at it from the human to integration standpoint. So that really has been beneficial all across the board. There's been, yeah, in this case, there's been nothing but positive comments on that type of feedback.
Are you able to comment on anything that you found in these projects, given that you mentioned that previously the analysis tools didn't necessarily identify certain things? Has this tool enabled you to find something that you were not expecting that you can maybe tell us that's really groundbreaking?
Yeah, something we did do that I can tell, and this is based from a presentation I did for MIT, is we actually did an exercise where we did kind of a study where we looked at, we did a analysis on one of our control loops, and then created and went all the way to creating requirements from those loops. And then we did kind of a comparison of another team that did use the traditional methods of those of creating requirements for the same activity. And we ended up, which was interesting, about 8% of the requirements were virtually identical. Then another 60% of the requirements we called found early, because in STPA you didn't need to have a design, and they had to, in the other test group, they had to create a design to find those requirements. And so we found those using STPA ahead of the other team by far because of the need for that. And then STPA found roughly 22% more or additional requirements that the traditional analysis didn't find.
That's really significant, isn't it?
Yeah, and so it is only one study, so it doesn't mean the results are always going to be the same. But even if it's half those numbers regularly, that's still huge.
Can you maybe explain or maybe share with us another project in the time that we have got left?
Well, one of the things that maybe I'll talk about a little bit, because STPA is really something that from most companies, including my company I work with, it is newer. But the analysis is kind of being used across the board. But STPA, where we find it the most interesting, is because you can use STPA only by understanding how you want to control something. It inherently is really beneficial up front, because if you say identify your controls and then find all the items that STPA brings out, which are primarily going to be safety issues, that will allow you to incorporate that into your design before you even prototype or create a design. So it all of a sudden means if you look at like a standard systems V and you put that up front, you're actually doing that, say at the same time you're doing your early FHAs and various things like that, you're actually able to say things that need to be in the design and start, say, adjusting things like back to the example I used, the simple one of the flight pitching up and pitching down. You're actually able to realize things that need to be incorporated early in the design, which does save huge amount of money up front, because the thing sometimes, which happens in a lot of companies, automotive and aerospace, is if you find something after, say, you've built a car or built an airplane, it costs a lot more to fix it at that stage, which is towards the end of the traditional systems V, where you're kind of doing your production verification and you find something, which isn't uncommon. But if you can prevent that and find that at the beginning of the systems V, typically saving 10 to 100 times the amount of money that it does to fix it at the far side, the production verification type part of the V towards the end. So that's really the usage that STPA seems to have very high value for.
So it's improving safety, time,
improves the design, in essence makes it less expensive because of finding things up front. And so those are all things that at least I love, and it incorporates the human, which is not from a systems engineering standpoint, that's relatively new. And to me, that's a huge important thing is getting that human systems integration so that we can get our human factors engineers and everybody working on those problems early, where they can have the most impact. Because even earlier in our conversation when we talked, if we have to, as human factors engineers, if we have to work with something existing, an existing piece of software or hardware, it makes it harder for us to put significant improvements in because the limitations to change. And so if we can do the more upfront, we can involve the human factors, the more we can get change in that really helps the human. And that is something I'm 100% for.
Thanks for joining us at the Human Factors and Ergonomics Hub, brought to you by the Human Factors and Ergonomics Society of Australia, where human-centred design really matters. If you like this podcast, make us your favourite in your podcast app. We look forward to chatting with you next time.